Following is an introduction to using file I/O using Python. First thing we'll look at is user input. Sometimes it's useful to be able to get to input variables from a user by prompting their response. So this is done simply with the raw underscore input, then you enter some text, and then it'll give a little box that the user can enter their values. Pretty simple to do. You don't normally do this with an IPython notebook because you've got the values that you can type in directly. But it can be handy for gathering information from another program that's running for some interactive behavior. The second we'll look at is NumPy file I/O. Very often we want to write data files. We might have an array of data and we simply want to save that array of data to a file. And we can do that really simply. NumPy provides functions that can do that. So let's first define two functions of time, y1 and y2. So we'll have an array of time, and then an array of y data, and an array of y2 data. We can combine these three arrays. So here we have t, np.linspace will go from 0 to 1 with 10 points. And then we'll just define y1 to be sine of 10t, and y2 to be sine of 10t times some decaying exponential function. We can combine all three of these single arrays into one matrix using the vstack function, which is a very useful function for combining arrays. So that'll let us stack t next to y1 next to y2, and to get the right shape of it, we'll transpose this resulting matrix, or this resulting 2D array. And we can print the shape of the data, and it comes out to be 10 by 3. So if we start with an array of 10 points with y1 and y2, the resulting data will be 10 rows and 3 columns. So we now have this single array called data, and we can save that using this np.saveText function. It's pretty easy to use. You just give it the name of a file and then the array that you're saving, and it will save that data in the file. So fairly straightforward to use that. And if we do that, if we go ahead and run it, then if we look at some of the output that it gives us, we can see the file is ty1y2.dat, and if we look at it, then it's got the data is saved in that file. Let's go ahead and run that again. There we go. And if we look at it, we simply get the raw output from the file. So 3 columns of data. It defaults to just separating the data by spaces, and you just get the matrix just like it looked. So pretty straightforward to use that. We can add extra arguments to the function by specifying like the file name, the data, and then you can add a format string if you want to format the data with specific values. We'll talk about that some more later. You can use a delimiter instead of a space. You can use a comma or a tab or any other character that you choose, and you put that here. You can give a new line character. You can give a header, a footer, and tell it how you want to start comment lines. So if you want more information, just hit np.saveText, txt rather, question mark, and that'll give you more information on the function. But here's an example. ty1y2.dat. I commonly will save data files with a .dat extension, just text files. There's the data I'm saving. I'm going to format it to have fields that are 18 spaces wide with 15 decimal points. I'm going to use a comma to delimit the sections, and then I'm going to have a header that has t, y, and y2 so that I know what the data is. And so if we run that, and then look at the file again, then we can see that it put a comment starting with a pound. It does that automatically unless you change it. And then the header that I specified, now we get data that is uniformly formatted and has commas that separate it. Notice that there's no space here. That's kind of annoying between the comma and the next line. And we could change that pretty easily if we just change the 18, maybe make it 20, run it again, and if we look at our file, it's got more space in it. Much nicer. Okay, so that's a pretty easy way to save values. You just need to use save text and give it the array of data that you want to save. You can read data into NumPy using the np.load.txt function, and it's pretty easy to use likewise. You just tell it the name of the file that you want to load, and then you can give it extra arguments if you need to. So in this case, I'm going to go my data equals np.load.txt, the name of the file. I'm telling it that I delimited the different entries by commas, and then when I load it in, I can see that the data gives me back the values, a 2D array. So you can save files, you can load them back in. NumPy has a native NumPy binary format that it can use, and that one uses the function called save. Similar to use, you go np.save file name and the array that you're saving. This file, you won't be able to read it because it's a binary file, but the file size is typically significantly smaller. So here we save, let's run it. Here I'm calling it ty1y2.npy, so as in NumPy. And if we try to look at it, ty1y2.numpy, it looks like garbage. We can't make any of this data out. But we can load it back in if we need to, if we just want to save the data, and we can load it with simply mydata2 equals np.load, give it the name of the file, and it'll load the data back in. So that works pretty well, and it'll typically be smaller. So if we look at the file sizes, ty, then we can see that ty1y2.dat was 651 bytes, and the NumPy version was about half as big. So that can reduce file sizes, which can be important if you save pretty large files. Okay, so it's convenient, this is a little bit off the topic of file I/O, but it's convenient to have access to a number of commands. Python will let you type bash commands. This terminal that I'm using right now is a bash shell, and you can tell it's bash because this cursor has a little $sign behind it. And some of the basic commands are ls will show you the contents of a file, pwd will tell me where I'm at, which directory I'm in, print working directory, and there's others. You can enter all of those commands in the IPython notebook and they'll work just as if you had typed them at a terminal, which can be pretty useful. So to give an example, ls shows the listing of files that are in your current folder. If you do ls-l, it'll give you more information. pwd will print the working directory. cat will show you the contents of a file. mv file1, file2 will move file1 to file2. So if I have a file called a.dat and I want to change it to b.dat, I'd type nv a.dat, b.dat. mkdir will make a new directory, make a new folder. rm will delete a file. rm-r is needed if you want to delete a directory. You can delete more than one file, rm, file1, file2, etc. You can move from one place to another with the cd command, cd for connect to directory. There's a special directory called .. and if you type cd .. it'll go up one folder. You can go up two folders if you type cd .. Folders are separated by a /. Star is a wildcard, like it looks like we need to escape that. Star is a wildcard like ls star.dat. So if I type ls star.dat, it shows me all the .dat files. If I do ls, it shows me everything. You should note though, if you can type them directly, but if you need to mix Python code with these commands, then you'll need to prepend the command with an exclamation point. Here's some examples. I can go to a new directory, cd .. /lecture14 file IO, and it goes there. Then I can type pwd, and the output is the location that I'm at on my computer. If I type ls, it shows me all the files that are in this directory. If I type ls-l, it will show me a more complete listing. If you do like ls-l, ls-lh, different kinds of commands here. You can type cat and then some file, and it'll show you the contents of the file. So we stored that one already, and we can see cat ty1y2.dat gives us the values in that file. So these are pretty useful commands that you can use, and you can prepend any of those with an exclamation point, and they'll work as well. So if we have Python code like x equals 5.5 and then type cat, it doesn't work, but if we put the exclamation point, it does, and that's because we put Python code in there. If we get rid of that, then that works, and that complains again, but this is because of the mixing the Python. So in general, if you just put an exclamation point in front, then that'll work a little bit better in all cases. So that's probably a better idea to do. And we can add those if we want. Exclamation point, exclamation, exclamation, exclamation. H will make this human readable, so these file sizes will tell us more information. 25K kilobytes, 62 bytes, M for megabytes, etc. There's a really useful function or library in Python called Glob, and it's really useful for getting a list of all the files that are in a given directory. So here I've got, you import it, import glob, and then I can go files equals glob.glob, star means get me everything, and then a list of all the files will be saved in here. So we can go print files, and it basically gives me a list where every element of the list is the name of a different file. So that can be useful if you want to process a number of different files. Or you can loop over each file using a for loop, like for file in files. Then for each H run through the loop, file will take on a different element of this files list. So here we're printing, do something with this file, and you can see how when we run this, we get file 1, file 2, input YAML, etc. So glob is a really handy, pretty easy to use command. Some more general file manipulation. We can input from a file using the readline function. So the input is, so we saw NumPy, but in general we can read and write anything we want in any kind of format we want using by opening a file handle here. So if we use ifile equals open file name, comma, this little quote R, this says open file1.dat for reading. So file1.dat should already exist, and we're going to open it so that we can read it. We can call ifile anything we want. You can call it input file. I like to call it ifile to denote an input file. And then we can read from that file into variables like s equals ifile.readline, or print s equals ifile.readline, print s ifile.close. So if we look at what this file is, what did we call it? File1.dat. We can see it has some header, some new line, this isn't a new line, and the third line. Okay, so that's what's in the file. And so if we go s, if we open the file and then go s equals ifile.readline, and then print s, the thing that comes out is some header, which is the first line of the file. Then read the next line, ifile.readline. If we do it again, then we get the next line, some new line, this isn't a new line. We can keep doing that if we want. Okay, so that's a simple way of using this file. After we open the file, it's good form to close the file. So when we're done with it, ifile.close. Go ahead and close it. So we open a file and close the file, and then inside we can use this readline command to grab the next line and put it in a string. There's a function called readlines, And the readlines function works by running ifile equals open. So we'll just open the file again like before. Readlines will take every line in the file and make a list out of it. So lines is a list where the first element is the first line, the second element is the second line, etc. So we can print it if we want to see what it has. Print lines, lines, and we can see that we get element 1, element 2, element 3 are those 3 lines. And then we can loop over those if we want. So again, for line in lines, print line. And we get, when we run that, we get some header, some new line, the third line. And this is just a list. Lines is a list, so we can print and use it as if it was like an array. So lines element 2 will give us this, the third line. And in fact, that's what we get when we print it. Print lines 2 equals the third line. So read line and read lines to get a single line or all the lines. Another useful function is called split. If we have a string, in this case the string is stored in a variable called line, we can go line.split and it will split the string into a list of words in the line. So we can print it out also, print words, and we can see it split the third line into words that are separated by spaces. And then we can loop over all those words if we want. For W in words, print W, and it'll output each of the words in succession. So those are 3 useful functions for inputting data from a file. For file output, we can do the analog of writing a file is reading a file. We go ofile for output equals open file1.dat with a quote W. The W will be for writing, and then we can go and write anything we want to the file with the write function. So ofile.write some header, ofile.write some new line, ofile.write this isn't a new line, ofile.write the third line. And then when we're done with it, again, ofile.close. Notice this \n. That means insert a new line here. So we want a new line character there. If we don't put that in, then the next time we write to the file, it'll just leave off right where we had it. So we do some header \n. We'll put a new line, some header, and then we get a new line. And as soon as we write some new line, that's fine, but we didn't put the \ in there, so when we write again, it goes immediately after it. So don't forget to put in this \n. It means new line. In some cases, you might have to use a carriage return also, /r, like /n/r or something. So we can look at the file cat file1.dat. We just loaded that file and we can see the contents of it. Here's another example. Here we'll open a file called file2.dat for writing, and we can type ofile.write this pound, which is a common comment statement, put a new line, and then for I in range np.size t, we're going to write 3 variables. This is kind of like that other example where we were writing the time y1 and y2 data, but this is a little bit more fancy version when we want to write formatted output of 3 variables to our file. And then we close it. So let's look at what this does. So we have this statement, then we have it again, then we have it again, and that corresponds to each of the 3 variables that we're writing. Okay, so we have a format string right here, and then we have after that the variables that correspond to it. The keyword here is this %sign. So let's look at this %12.5e \t and see what that means. So the % indicates that we're going to put a code variable in that spot. So when the computer comes to a %, it goes, oh, you are going to insert the value of a variable there. And so we need to have, and that's going to be TI that it's going to insert. Then it comes to the next one and goes, oh, I see another percent. Put the next variable in there. Then it comes to another percent, stick the third variable in there. So the percent means insert the variable when you see a percent. The 12.5e, that's a formatting statement that says I want room for 12 characters, and I want 5 decimal points, as in 0.5. 12 is the total width. 0.5 means 5 digits after the decimal point. And E means I want it in scientific, that is exponential notation. So if we look at that file, let's go ahead and run this. And then we can look at file underscore 2.dat. Whoops, dat. What did we call it? File underscore 2.dat. There. Okay, so this first line here is the comment that we put in. Right there. And then after that we write all of the arrays of t, y, and y2. And we can see that we have space. Let's count up the number of spaces. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Whoops. And then we have a tab. So there was 12, and that's what we told it. We wanted 12. And we want 5 digits. 1, 2, 3, 4, 5. So we've got what we wanted, and then we end it with a tab character. \T stands for a tab, and you can see the cursor jump due to the tab character there. And then we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Oops. We have tab, and then we have a space. So let's see if that makes sense. Tab, space, and then 1, tab, space. Then we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And tab, space, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that's what this formatting means. And then the last one, instead of a tab, we'll put a new line character, /n, so it'll go to the next line. Okay. Another example would be you can mix text in there. So ofile.write, here is the value of x : %g, and then when it sees a percent, it wants to put a variable in there. There's the variable x. And G is a different kind of format statement. We'll look at that in just a second. So we've seen a couple of these format codes already, this %g and this %e. Here's a summary of these codes. %s for string, %r is also for a string, but it'll convert any kind of Python object. It doesn't have to be a string object. %c for a single character, %d for a signed integer. You can also use %i, like 1, 2, 3. %f for a floating point decimal number, %e or %E for scientific notation, and %g is a pretty version of the output, and it figures out the output that looks best. So it'll do %e if the exponent is greater than -4, otherwise it'll do %f. So it figures it out for you. There's some examples at this website in the link. We won't look at those. Suppose we write pi and the gas constant. We can type pi equals %20.8e %pi. That'll give us a field that's 20 characters wide. We want 8 decimal points, 8 digits, 20.8, and then it's scientific notation, in this case e to the 0. We can do pi equals % and just write .3e, and that'll give us basically scientific notation with just 3 digits. We can write a regular floating point number, pi equals %f. In that case, it's going to just default to its own prescribed version of the number. So we gave it lots of digits, but it's not outputting all of them. It decides how many it wants to output. If you do %.2f, it'll say, give me it with 2 digits. If you do pi equals %g, it'll figure it out for you. You can also chain these up. You can put multiple values. So if we say, let's let the string s be pi equals, then we can go print %s %g. It wants a variable that's a string. It wants another variable that's some general number. And then we tell it what the variables are. S, which is the string we stored, and pi. We could have called this whatever we want. SSS, SSS, and it'll output it for us. Here's another version, print pi equals %.5f and rg equals %10.5e. There's a percent and there's another one that wants two variables. It's going to stick in pi and with 5 digits in a floating point format. Here it's going to do 10.5e, a little more space, with 5 digits on the gas constant. And we can also do another example here, YYZZ. This one kind of illustrates how this %g pretty formatting works. So if I give it too many decimal points here, 0.00018 to the minus 5, then it'll default to exponential notation. But if I give it to it with 1e to the minus 4 here, then it'll output it with regular floating point notation, just to illustrate that. We've been using a lot of this Python 2.7 version of the print statement. The newer Python 3, you should use, the print requires to be used as a regular function, so you'd want to use parentheses around it. And you can use all these same formatting with the print. So the value of pi equals %g, end quotes, and then parentheses pi. That'll give us our values. So let's switch gears a little bit. There's for inputting files from data, so that's a little bit about writing data to files in a formatted fashion. It sometimes happens that you want to be able to read in data from a formatted file, but you don't want to have to figure out how to do all the reading yourself. There's some specific file formats that you can choose from, and YAML happens to be a very nice input file format. It's really useful for setting variables in a file that you want to then read as parameters for running a code. Many research codes work this way, where you write all your parameters and variables that you want to use into a data file, and then you read those in. So that way you don't have to change your code. You can just change a text file and then read in the data from that text file. There's a wiki page for YAML that you can find more information about. Here I'll just give you some of the basics. In Python, you would just to use YAML, you type import YAML, and below will give a sample file. So here's an example file from one of my research codes that we have. The syntax is pretty straightforward, much easier than formats like XML, for instance. Basically, blank lines are ignored. You put keywords like variables that end in semicolons. You can put comments in that begin with the hash symbol like usual, and we can use aligned indentation to indicate nesting groups. So here I have this group that's called params, and all these variables, seed, tend, row 0, etc., all sort of belong to this subgrouping of params, which is useful. You can include arrays of data. So here's a one-dimensional array of data, and this dash sign with a space after it is used to set off the individual elements as if they were bullet points. You can also do 2D arrays of data, and in this case, that's really a 1D array of data, but each element is itself an array, and that gets you a two-dimensional array of data. So in this case, you'd have a dash space and then just put brackets around it to indicate a list. And these would be a comma-separated list of values. Then you can read this file. You can read values from the file in any order. You can read them as often as you want, and you can choose how many of them you choose to read, which is significantly easier than trying to grab data from this file if you were just trying to write a generic input file. YAML provides all the tools for you, and I'll show you that in just a minute. So suppose we wanted to read in the value of the seed variable or the tend variable, or we want to grab this array of XY data or this array of times, or we want to find the concentration of C3H8. In YAML, we would do that simply by typing import YAML. Then we need this slightly different notation for opening the file, and you could copy that. And then to grab a variable is as easy as typing, like, name it something, seed equals my or Y file. So I'm storing this YAML input file in a variable called Y file. So we go seed equals Y file, and then we treat it as if it was just like a NumPy array, for example. So that we've got Y file. Well, I mean, it's 2D, but these nesting levels are indicated with the brackets. So if I want the seed, we can see that seed is below params. So we say, okay, Y file bracket params bracket seed. Y file bracket params bracket tend. And the same for any other variable. And if we print those, we can see that in fact seed, it reads the file, and it reads seed is 23, just like we wanted. So with very little code, we're able to open the file and grab the data without having to write lots and lots of formatting data. Because the alternative to this would be like ifile.readline, 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 and on every single read you'd have to search to see if you happen to come across the seed keyword. See, that would take special code to do that. And then you'd have to break this line into parts using maybe the split function, and then finally get the value of 23. In this case, we can do all of that with one simple line, seed equals Y file params seed. Tend equals Y file params end. If I want the O2 concentration, the O2 concentration lives down 1, 2, 3 levels. So we simply go O2 constant, we go YO2 equals Y file stream props comp 0 O2, and it'll grab that concentration, the value here being 0.21. So that's what we get, 0.21 for the O2. We can grab the whole array by simply writing dump times equals Y file dump times, and it'll grab all of this data here into the array. And if we print the dump times, we can see, yep, it grabbed all 4 values. Easy peasy. And we can even grab the 2D array just as simply. Here we have XY data equals Y file init params vprof, and it'll grab the vprof array of data. So this can be really, really easy if you're writing a project, for instance, where you want to put heat exchanger data, for example, into an input file and then grab the data from that input file so that you can then operate on the variables. And that's all we have.